Hi there, this is Manuel from Entagma. Welcome to a new free tutorial, the first free tutorial after our Patreon launch last week. Today I want to talk about the space colonization algorithm used by Adam Runions to model trees. There are many different approaches in modeling trees, for example recursive solutions like iterated function systems. And then in 2007, Adam Runions presented this novel approach that focuses on the competition for space. So with this algorithm, it's possible to model branching structures like these here with simple parameters. It's a very beautiful algorithm, and today I want to show you how to implement this inside of Houdini with VEX. But before we dive into Houdini, first let's have a look at some theory. Here you see a graphical overview of the algorithm. This is inspired by the graphics you find in the paper, so have a look there if you need detailed information. Let me walk you through the steps of the algorithm. This is not the very first iteration of the algorithm, but it's some iterations into the execution of the algorithm. Some nodes have already been created. These 6 black nodes here are the ground structure. And then there are these 4 red attractor points. These attractor points are scattered in space and define where the structure is allowed to grow to. The first step is that for every attractor point a search is performed for the closest node of the structure. So every attractor point here in B finds the closest node, and then it's associated with this node. So every node stores the information which point found it. That means that every node can have more than one attractor point associated, but every attractor point only has one closest node. Now directions are computed, here in picture C. In this case, this is easy because there is only one attractor point and we have only one direction. We form the vector between this attractor point and this node here, and then we normalize the vector to get a direction. In this case, we have 3 attractor points, so we take the vector to all of these attractor points, normalize the vectors, then sum them up and normalize them again. This gives the mean direction. And now it's time to create new nodes and to grow the structure. And this is done by using these computed vectors. That is the direction we want to grow in, and we create new nodes in the direction we computed at a distance from the old nodes that is exactly the diameter of one of the nodes. These red circles indicate where new nodes are placed. Before the whole algorithm is iterated, we do one final step, and that is we remove attractor points that are close. We pass a parameter to the algorithm called the kill radius, and all the attractor points that lie now inside of this kill radius are removed. This is true for this point 0 here. It's inside of this blue circle, and that's why it's removed. We do that not to recreate connections over and over again. In the next step of the algorithm, everything is repeated, and that means that this node here will again be associated with these 3 attractors, and will probably create a new direction vector that is very similar to this one. Then a new node will grow here, and after that this attractor here with the number 2 is very likely to be removed. And by iterating this algorithm, a very beautiful structure emerges. So here we are inside of Houdini. I already imported a model that I want to use for the algorithm. I created this in 3D code. It's a quick doodle that gives nice structures, and I imported this as an OBJ file using a file node. We want to use this as a basis for our growth. The first step is to fill this model with attractor points, because we want to give the algorithm a hint where in space it can possibly grow. Instead of scattering points directly onto the model, we want to first convert this model into a volume because we want the effect to be volumetric. You can do it on the surface, it's beautiful on the surface too, but in this case I want to do it in the volume. So let's create an ISO offset, append it here, make my parameters visible, and switch the viewport to dark because with volumes it's easier to see. Now I up the resolution, in this case to 200, because we want quite a precise representation of our model. And I usually append a volume visualization and up the density just to be able to see this better. Now here we have our volume. Now we can scatter points into this volume by appending a scatter, like so. Let's turn off relax iterations, because in this case we actually like the random placement of the points. And let's say we scatter 100,000 points, like so, to fill the shape quite nicely. But this looks a little bit boring. I think it might be more beautiful if we vary the density before scattering points. So let's do this by creating a volume VOP. Put it here in the middle, the volume VOP. To use the volume VOP, we first have to name the volume. Let's name this volume density. I use density because the volume VOP already has an output for density. It's just the default. You can name it however you like, and then to access the values or to write to the values, you just create a bind export and use the name you used before. But I just use density because it's convenient. Now that we have the value export in place, let's create some variation using anti-aliased noise. Put on AA noise node and connect P to position, such that the node knows where to sample the noise, and after that I append a fit, because the anti-aliased noise creates a noise in the value range of -0.5 to 0.5, but we need values in the range of 0 to 1 because this is density. So just put -0.5 and 0.5 here and remap the range. Let's up the frequency to say 10 and maybe give it a little bit more roughness. And now let's append a ramp parameter to be able to remap the result artistically. I call this ramp noise and switch it to a spline ramp. And now we want to set the density, but we only want to alter the density that is already there. So what we need to do now is to create a multiply to be able to use the incoming density as a mask. So multiply the result of the noise with the density. That means where no density is present, the noise will just be multiplied down to 0 and will not show up. And now connect this to density. Up one level, you don't see anything, and that is because the noise ramp is set to 0 by default. Let's go to the volume visualization and append it here to see the results. And now we can just go up with this ramp here. And by moving these two knots closer together, we can create a quite interesting structure with holes in it. Now if we switch to the scatter, you see you have now a far more interesting shape, and you can just alter it by using this curve. Something like this will do. Now let's put all these points inside of a group, because later inside of the solver we have to distinguish between attractor points and seed points. So points where the growth actually starts. So let's name all these attractors and maybe append a color to give them a color to later be able to distinguish easily between them. Let's say we make them blue, like so. But we have a problem here because we have now gaps in the structure, and the algorithm is dependent on attractor points being present. So gaps are not good. A variation in density is good, and we of course could try to put some points here, but I used a different strategy by just using a second scatter node, and I append this directly to the ISO offset. Let it create 10,000 points, and then just merge these with the other ones, like so. Put them in the inside of the group here, but you have to switch the group to points to work. And now we have 110,000 points inside of the attractor group after this color node. Let's clean up the network a little bit. Maybe put the volume visualization on the other side, switch the wiring type like so. Okay, now this is prepared. Now let's create some seed points, because we need locations in space where the growth can start. I use the add node for this. The add node allows you to just add points in space. Just tick on here, 0 and you have the very first point. And if you then use the manipulator, you can move this point around in space. And we want to put this in a group too. So create another group node and switch this to points. And I call this nodes because this is the group where all the growth will happen and where the nodes will accumulate. And then another color node, just for visualization purposes like so. And now we can merge both geometry streams together, because for the solver we need everything in one stream. At the moment our seed is here outside of the structure. That is not good, because we will have to place it inside of this attractor point structure. So let's quickly do this. Put it somewhere where the attractor points have the chance to find it. And maybe let's create a second one. Just click this plus here and you get a second point. You can start somewhere inside this structure here, for example, and maybe even a third one, because then the growth will just happen more quickly. Like so, maybe. Now that everything is prepared, the fun stuff comes. Let's put down a solver and connect the geometry stream to the very first input. Dive inside. Inside you find 5 nodes. This one here serves the geometry from the previous frame, and these 4 are just the 4 inputs of the node. So now let's implement our algorithm as planned before. And we do this by using wrangles. So put down a point wrangle and connect it. The very first wrangle that I write is called init associate. We want to use a quite new feature of Houdini, and that is array attributes, because I want to make all the attractor points search for the closest node. But then the information of this search, the result of the search, has to be stored on the nodes, and I will store the result into an array. And this array has to be initialized. That is what I want to do with this node here. So press Alt-E to open the VEX editor, and let's write I square brackets add associates is array and brackets. What this says is the I stands for integer, like with every attribute you create. And then these square brackets indicate that this is not a standard attribute, but an array attribute. Then the @ sign just stands for attribute, and then comes the name. And I have to initialize this with the statement array. This is a function returning an empty array. So every time the solver runs, the attribute will be initialized with an empty array. That is very important, because in every step we want to fill this array later on with new values. Now I have an array here, associates. These brackets indicate that this is an array attribute. Okay, now let's actually associate the attractor points with the nodes. So another point wrangle, connect it here, and let's call this associate. And very important is that I want to make this point wrangle here run only over the points in the attractors group, because this should just search for the closest node to every attractor. So I don't want to search on the nodes, but only on the attractors. Alt-E again, and let's code this up. First, let's define a parameter that is needed for the search, and that is the search radius. I call it infrad. That is from the paper, where it's called influence radius, and just use a channel function infrad to create a new parameter. And now we do the search. So integer near point, and in this case I use near point instead of near points, because I'm only interested in the nearest point, is near point, brackets and semicolon. Geometry stream is 0, and now I pass on the nodes group, because I only want to search in the nodes group, not in the attractors. I want to search around the location @p, because remember we are currently running over the attractors, so @p is referring to the current position of the currently processed point, and then infrad as the search radius. This will give us the ID of the point that is closest. And now for our array. I create a new local variable called value array valar and use the array statement to create an array from ptnum. That is necessary because I cannot store an integer value into an array attribute. I have to store an array into an array attribute. And by this statement I create an array with just one value in it, and the value is the currently processed point, because that is the information I want to store in the point I found. So let's do this with setPointAttrib. And I use pointAttrib geometry stream 0. I want to write to associates, because this is the name of my array attribute. Then I want to write to the associates attribute of the point that I found with near point. I want to write the val r. And now, very important, instead of using set, what I use normally, I want to use append. Why is this? Because more and more attractor points can, in theory, find the same node. And by using append, I make sure that the results from the previous search are not overwritten by the next one, but the results are just appended, so a list will form and the array will grow longer and longer, and eventually will contain all the associated attractor points. So press apply and accept. Looks as if we don't have any errors. Now press this button here. I make this pane a little bit bigger, and you see that this created the infrared parameter and set this to 0.03. So now let's grow the structure. Another wrangle is necessary for this. And this time this will run over the nodes group. Because now we stored all the information on the nodes, and now we only want to execute the nodes. Oh, it looks as if we do have an error here. Let's quickly fix this. It looks as if I again forgot a comma here after nodes. Press apply and accept, and the error is gone. So now the next one will be called expand tree, because this is what this wrangle is intended to do. Press Alt E and let's code this up. We need another radius. In this case, I call it rad, channel radius, and this is the diameter, or the radius, well, the diameter of the individual node, so the size of the node. It's basically p-scale, because I need this to be able to determine the distance that I use to place new nodes. Now I want to read the information that I gathered earlier, that is the associates information, and I will put it into a local variable, so integer my associates, and this is an array, will be I for integer, and then array attribute associates. So now I just read the information from the attribute and put it into a local variable to work with it. And now I want to gather the information about these associates for all the associates. But I only want to do this if associates are present. So let's put a quick if statement here. If the length of this array is bigger than 0, so only if there are actual associates in this array, please only then do stuff here, enclosed by these curly braces. And if this is the case, what I will need is a vector called sum that I initialize to 0, that will be used to accumulate all the vectors in case we have more than one associate. Now that I have this vector, I put a for each loop, because now I want to run over all the associates that are inside of the array. So I call this node my associates, and again brackets. And then we first need the position of the associate point. So vector pos, node pos, is a point expression or point function, finds the position for me. Geometry stream is 0. I want the attribute p. Make sure to enclose it in quotes, and then node is the ID that I want to read from. And then the vector dir for direction is the normalized version of the difference of this position of the associate node and myself, the seed node. Okay. And now I add this direction to the sum. I use plus equals, which means take the sum, add the direction to it, and then return it and store it in sum again. After that, I have a vector that stores a sum of all the individual vectors to the individual associate nodes. But remember, we wanted to normalize this vector again. So let's do this. Sum after the loop is normalize sum. Now I have my average direction. And now it's time to add a new node. So integer n node for new node is add point. And this point has to be added to the geometry stream 0. And where do I want to add this point? Well, I want to add it where the old node was, so add p, but plus the average direction vector, sum, which is normalized, so it has unit 1. And that means I can just scale it by rad, which is the diameter of the individual node or particle, and I will reach a location that is exactly 1 diameter apart from the old node, but in the direction I found, like so. Now I have a new node. What's left is to make this node be a member of the node group, so set point group. For this new node, geometry stream is 0, the name of the group is nodes, and then n node for the ID I want to use. Then 1 is a value to make it actually a member of this group, and then set, because I want to set this. And after that I just quickly add a color. The syntax of add point attrib is very similar to set point group. So I want to set the attribute cd, and I want to set it on the new node. I want to set it to red, so let's create a vector red. And don't forget to state that you want to set this, like so. Okay, great. And what's left now is to add a polyline between these points. In case you use a radius for the actual radius that is really the geometric radius of your individual points, it's not necessary to connect them with polylines. But in case you use a larger radius, so have points be spaced apart a little bit more, then it might be beneficial to have a line connecting these points. So let's quickly create this line. Integer and prim for a new primitive is add prim. The geometry stream is again 0, like so. And then I have to state that this is a polyline, so an open polyline. And as we did in the last tutorial with the connect the yarns solver, let's add vertices, add vertex, to make these points members of the primitive. Geometry stream is 0, n prim is the primitive, and the first point is ptnum, the currently processed point, and then a second vertex, same geometry stream, same primitive, but new node, because this is our new point. So, fingers crossed. Press apply, and of course here are the errors again. Like always, what is he telling me? Here I have this little red indication where the error happens to be, so set point group, and I missed another comma, and of course another comma was missing. And then, last but not least, it is beneficial to spell add vertex correctly. Now everything compiles without errors. Don't forget to actually create the parameter that we defined in code by pressing again this button. Then I get this rad parameter, and I set this to 0.002. That should be the diameter of my particles. Okay, almost done. One wrangle is missing, so the 4th point wrangle. Connect it up and call it remove attractors, because now we want to clean up after the process. And this will run over the nodes group again, because the nodes will search in their proximity, and if they find an attractor point that is close, they will remove it. Press Alt-E, and let's start coding. We need another radius, this time the kill radius, so float killrad is channel killrad. This is from the paper 2, the naming. And then int near points. This is an array. I want to find all the points that are within the kill radius. And this time I use the near points expression again, or the near points function, because now I want to find all the points, not only the closest one. The geometry stream is 0, and then the group to search in is attractors, because I now search the other way around at P. And again I forgot a comma, but this time I see it directly. And then killrad, like so. Now we find all the attractors that are within the kill radius around the individual nodes. And then just for each, to run over all the found points, integer point this time, near points, and brackets. And we don't have much to do here, it's just that we want to remove point in the geometry stream for all the points we found. So with this for each loop we are telling the system to remove everything that is within the kill radius around the nodes. Apply, accept, and this time no errors because I found the comma directly. Okay, now let's click this button to create the killrad parameter, put 0.01 here, and now the big moment has arrived. Go up one level and press play, and look what's happening. It's beautifully growing inside our structure and forming a very nice tree-like branching structure of big complexity. I really love this algorithm. Let me quickly turn on anti-aliasing for you to see it better. Look how intricate the structure is. And by varying the distribution of points, you can really alter the shape and make it exactly the way you want. And it reacts to these radius parameters too. So the bigger the search radius is, or the inf radius is, the smoother it will be. It's probably a good idea after the solver to append a smooth node, because this way you can smooth out the positions a little bit, like so. And here you have it. Space colonization inside of Houdini. And it's quite fast too. So thanks a lot for following this tutorial. I hope you learned something as always. And today, for the first time, a very big thank you to all our patrons on Patreon, especially Mohamed El Abri and Nick Wood. Thank you so much for helping us. It really means a lot to us.